everyone. Welcome, friends, to our stargazing lecture for the month of November. I'm Dr. Cameron Hummels. I'm a computational astrophysicist here at Caltech, and I will be your host for this evening's event. We've got a super exciting event about black holes from a famous as astronomers get, famous astronomer who was in the news a bunch in the last year for this discovery she's going to talk about tonight, Dr. Katie Bouman. And I'm excited, I don't know about you, but I'm excited to just talk about space for the next 2 hours, since this week has been so much turmoil associated with the election and all of the chaos surrounding that. So I'm excited to talk about space. I hope you guys are too. So a quick briefing of our schedule for tonight. After a few brief announcements by me, I will quickly show a view of what the sky looks like tonight from latitudes akin to Los Angeles, because these are normally have a stargazing component when we do them in person at Caltech, but obviously since the pandemic and we've gone to this live YouTube format, we haven't been able to do that. So that's kind of a virtual way that we can look at the sky. And then I'll introduce our speaker, Katie Bouman. Tonight she'll give roughly a 30-minute lecture on the discovery and imaging of the first black hole. Well, not the discovery, the imaging of the first black hole. And then we will immediately go into a Q&A session consisting of Katie, myself, and two other members of the department, Nitika Yadlapalli and Jordan Moxon, who work on a variety of different other topics. And we're just gonna be able to handle questions, or hopefully be able to handle questions from you guys on the topics of black holes, but also anything related to astronomy or physics or space science. Hopefully we'll be able to address it. If you like these events, we have 5 years worth of events that are on our YouTube channel, so check them out. We also have a sister series called Astronomy on Tap, which is a bit less formal. It's traditionally held in a bar, but we do it again over YouTube Live once a month, and have a couple of informal talks by researchers on their science topics, and enjoy a beer or a drink. And there's pub trivia too, which is super fun. Let's see. Our next Astronomy on Tap should be, I need to check the date. I think it'll be the week after Thanksgiving, so in a few weeks. Those are on Monday nights. And our next stargazing lecture should be about a month from now in early December, given by a young professor in the astronomy department named Dr. Vikram Ravi, which should be really good. Another quick announcement, you may have noticed in the news, beyond all the election news, there was a big science result associated with the discovery of the origin, the source of what's causing fast radio bursts. So this has been there were a few Nature papers. And just to quickly point out, much of that is about the discovery that was made by Chris Bohenik, who's a graduate student in Caltech's department. And he was actually one of our speakers at Astronomy on Tap 2 weeks ago. So I encourage you to check out our Astronomy on Tap from a couple of weeks ago and hear about that amazing discovery that's blowing up the airwaves right now. I think those are my announcements. So I'm going to quickly show, as I said, traditionally these events had a stargazing component. So I am just going to quickly show what the sky looks like right now. Hopefully you guys can see this. This is an open source tool for visualizing the sky called Stellarium that operates on Mac and Windows and Linux, and it's totally free and open source. And so this gives you an idea of what the sky looks like. Obviously, you can see the cardinal direction. So if you're looking up, it goes, instead of northeast, southwest, it goes northwest, southeast. And you've probably seen, and I've talked about this in past months, a couple of reasonably bright, what look like stars in the southern portion of the sky about this time. Those are actually Jupiter and Saturn. Jupiter's the brighter one, and Saturn is just off to its left. So if you have a telescope or a decent pair of binoculars even, you can zoom in with those and magnify your view and be able to tell, for instance, here, I'll just zoom in really quickly, that Saturn, you may be able to see its rings, or you may just see that it's kind of oblong and it looks like it has kind of ears. You probably don't have this good of a view, but you may, depending on the telescope that you have. Similarly, if you zoom in on Jupiter, which we will do here. If you have a really decent telescope or set of binoculars, you'll be able to see the banding structure on Jupiter pretty well. But the more obvious thing is you should be able to see a few dots, in this case, 4 dots. They look like stars that are in a line around Jupiter. Those are 4 of the largest moons around Jupiter, called the Galilean moons, because Galileo was the first person to observe them with his telescope about 400 years ago. So that's really cool to be able to see. But kind of the highlight of the sky right now is the Andromeda galaxy, which is quite visible near the zenith around now. Gotta really zoom out here to be able to see it. So yeah, near the zenith. And for those of you who don't know, Andromeda is our nearest kind of massive galaxy that's really similar to the Milky Way in many ways. It's like our sister galaxy. And yeah, you probably won't, again, unless you have a really super awesome telescope, be able to get this kind of resolution, but you will definitely be able to see kind of an extended object that looks kind of like the Milky Way. You can't really resolve the individual stars in it. It just kind of makes a milky, creamy band across the sky. And it's really spectacular to look at. I was in Death Valley last weekend, and even with a 10-inch telescope, you could very easily pick out this and start seeing some of the dust bands, and even see, I saw M32, not M110, but these dwarf galaxies that orbit around it. So really cool. Definitely check it out. And the darker the skies, the better. But even an inexpensive telescope, like I like manual Dobsonian telescopes, they're usually pretty inexpensive and have really good observing capabilities. So, okay. Katie, can I have you turn on your camera? Awesome. Okay. Hi. Welcome, Katie. Very nice to have you join us. I'm really excited about your talk, and I'm really excited about the Event Horizon Telescope's discoveries that are ongoing, but of course that really came out a couple of years ago. So, okay, so I'm going to introduce Katie. Dr. Katie Bouman is a Rosenberg Scholar and an assistant professor in the Computing and Mathematical Sciences, Electrical Engineering, and Astronomy departments at the California Institute of Technology. Her research focuses on computational imaging, designing systems that tightly integrate algorithm and sensor design, making it possible to observe phenomena previously difficult or impossible to measure with traditional approaches. This work led her to be a key member of the International Event Horizon Telescope collaboration, which in April 2019 imaged the first ever picture of the Messier 87 black hole 55 million light years away. Dr. Bauman's group at Caltech combines ideas from signal processing, computer vision, machine learning, and physics to find and exploit hidden signals for both scientific discovery and technological innovation. Dr. Bouman received her undergraduate degree at the University of Michigan and completed her master's and PhD at the Massachusetts Institute of Technology, i.e. MIT, in Cambridge, Massachusetts. And she was formerly a postdoc at the Center for Astrophysics at Harvard-Smithsonian. And you probably remember her from the wave of media response that she got associated with the Event Horizon Telescope's huge discovery of making this first ever image of a black hole. So thank you so much for joining us, Katie. I'm really excited. I'll let you take it away.
Yeah, thanks so much for inviting me today. It's an honor to have been invited, and it's really fun hearing about Cameron talk about the night sky. So I look forward to when these meetings can be in person again, because I'm really looking forward to joining and doing it. Yeah. But today I'm going to tell you a little bit about black holes and how we were able to take the first picture of a black hole. So black holes are, one of the most mysterious objects or things in the universe, and they're cloaked by this event horizon where extreme gravity is preventing light from escaping them. Yet actually the matter, as it's falling onto the event horizon, it's actually superheated to hundreds and billions of degrees, so that before it passes through that boundary, it shines really brightly. And for that reason, although black holes are relatively small, they can still outshine the starlight of all the stars in their host galaxies. And scientists have been studying black holes ever since they were first predicted by from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying the giant elliptical galaxy that's at the head of the Virgo constellation. This galaxy, which is called M87, is 55 million light years away from us, and it's very special. And that's because over 100 years ago, someone actually discovered a streak of light on the sky, which ended up being this galactic scale jet of plasma that is shooting out of the core of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists have tried to develop better and better instruments to try to study the supermassive black hole predicted to be in its center. And then in April of 2017, we hooked up this Earth-sized telescope and collected the data necessary to make the first picture of a black hole. And 2 years later, after processing the data, this is what we saw. So this black hole image was the result of a group of hundreds of astronomers, physicists, mathematicians, engineers, computer scientists from all around the globe who were able to work together to build an Earth-sized telescope necessary to take this first image of a black hole. And so today I want to tell you a very abridged story of how we were able to take that picture and how did we verify what we recovered, and also a little bit of hints of what is next. So the first question you might ask is, how are we able to take a picture of a black hole that by definition doesn't let light escape? So it should be unseeable. Well, light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is curving space-time. The photons can even go in complete circles around it. So the space around a black hole is lit up by this hot gas that's spinning around, as I said, heated to hundreds of billions of degrees. And so we have all these photons flying around everywhere. And some of them fall into the black hole. They're too close or they're pointed towards it and they fall in, but other ones just graze it and they're bent by the gravity of the black hole, such that the net effect is that basically that the black hole casts a shadow on the bright surrounding emission that's almost perfectly circular. And if Einstein was right about general relativity, this light would be bent into a ring whose size and shape tell us about the mass and the spin of the black hole. And this is referred to as the black hole shadow, because we're not actually seeing the black hole itself, but the imprint of the black hole. And so simulations of turbulent plasma in the jets and in the accretion disk around a black hole predict that if we could see at really, really high resolution, and we could see at about a 1 millimeter wavelength, we expect to see something like this. But even if the black hole does make this imprint, taking the picture of the light bending around the black hole still seems nearly impossible. And that's because the size of this ring is incredibly small. It's about 40 micro arc seconds in size, which is about the same size as a grain of sand. But if that grain of sand is in New York and I'm viewing it from Caltech in California. So taking a picture of something that small turns out to be really, really hard. And that's and the reason can be explained with a simple equation. You might know about this from your experience with your own telescopes. But the resolution, when you ignore the atmosphere at least, all comes down to a simple equation, the phenomenon of diffraction, which says that there are fundamental limits to the smallest objects we can possibly see. And this governing equation says that in order to see smaller and smaller, we have to make our telescopes bigger and bigger. And so if we plug in this, the wavelength and the required angular resolution that we need in order to see that black hole shadow into the diffraction limit equation, we can easily calculate that in order to see a black hole ring, we simply need to build a telescope that's 13 million meters across, or essentially the size of the Earth. And if we could build this Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. Well, okay, although building a single dish telescope the size of the Earth isn't possible, by joining telescopes located around the world, I've been working as part of an international collaboration called the Event Horizon Telescope Collaboration that built a computational telescope the size of the Earth that's capable of resolving structure on the scale of a black hole's event horizon for the first time. So we come up with a new kind of telescope, this computational one. And so how does that work exactly? Well, let's first imagine we could build a telescope the size of the Earth. A radio telescope essentially just acts like a giant mirror. And so light from the black hole, it's going to travel to this giant mirror for 55 million years, and then it's going to be reflected off of this parabolic dish, and all the light is going to combine together at that focal point. And the fact that we can combine light from across the whole dish allows us to have that very high resolution that we can see. But now let's imagine that instead of building an Earth-sized dish, we instead laid mirrors all across the Earth, essentially turning the Earth into a giant spinning disco ball. Well, then we could collect the same light at each of these tiny little mirrors, record the light that we see at every location, and then we could combine the individually collected light in a computer to make a picture just as good as the original Earth-sized telescope dish. But what happens if we remove most of the mirrors so only a few of them remain? Well, that is exactly what the Event Horizon Telescope has to deal with. And so all of the telescopes in this worldwide network actually work together. They're linked through the precise timing of atomic clocks. And so we have teams of researchers that travel out to each of the telescopes, and then we freeze light by recording petabytes of data. And then we use our computers to act like a lens to bring the light together to make the final picture. And so although some of my greatest experiences working on this project has actually been going to telescopes and helping out with observations, my work, both in the Event Horizon Telescope and more broadly in my group at Caltech, is actually on using computational methods to fuse information from sensors to recover images and hidden information. This is an area called computational imaging that brings together ideas from signal processing, computer vision, machine learning, and physics. And so my primary goal in the project is on developing algorithms to fuse the data from telescopes to make a picture and validate those images. And so for that reason, I'm going to give you a bit more of an abridged version of that. There's lots of different angles to this black hole story. So I'm going to talk a little bit about the imaging angle of how do we make that picture? How do we combine that information to make a picture? Well, first, to get measurements from the telescope, as I said, we record all this data. So we record hundreds of terabytes of data at each of the telescopes. Here you see my friend Lindy Blackburn posing with about half a petabyte of data that we collected at just the telescope in Mexico. And we record so much data that we can't send it over the internet, and so we fly it to a common location. And then at that common location, we use a special purpose supercomputer called the correlator that combines the precisely timed data. And then once that is done, this is passed to a calibration stage, which finds weak signals hidden in the correlator output and tunes parameters to extract a stronger signal. But the question remains, okay, this is how we are able to get measurements in the first place, but the question remains of what do we take these, what do these measurements tell us, and how do we use them to form a picture? Well, unlike with the camera, in the Event Horizon Telescope, we don't capture the picture of the black hole in pixel space, but instead in another transformed space called its frequency space. So for those of you who are familiar with what a Fourier transform is, we essentially take measurements of a black hole image's Fourier transform. If you don't understand what that means, that's okay. I think you'll get the main point still. So if you put telescopes all across the globe, you tile the globe in telescopes, you sample all the possible measurements that you can take, but since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out that for every 2 telescopes in the telescope array, we obtain a single measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. And so that's, when we only have a small number of telescopes, that's a very small number of points to try to make an image from. But luckily, as the Earth rotates, we actually obtain other new points. So since the projected baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in this measurement space. And so, okay, so what do these measurements tell us? Well, you can think a little bit about the measurements we make from the telescopes a little bit like notes in a song. So each measurement corresponds to the tone of one note. And the measurement at a different location is a different tone. So watching the black hole with the Event Horizon Telescope is a bit like listening to a song that's being played on a piano that has a lot of broken keys. It's definitely not perfect, but a lot of times there's still enough notes to follow along the song, to try to figure out what the song is. And so just to make this a bit more intuitive and help drive the point home, what I'm going to do is I'm going to play a song, and I'm going to let you hear the song as if we're adding telescopes or little mirrors to the Event Horizon telescope. At the beginning, you're going to hear only a few notes of the song, and as you go on, you're going to hear more and more notes until eventually, hopefully, you'll recognize the song. And I'll light up the notes corresponding to the tones we're playing on the piano keyboard, so you can just so you can see kind of what notes we're hearing. So I'll start playing it, and play a little game with yourself to try to figure out when you can start hearing it.
It's hard to hear, Katie. Katie, I don't think we can hear the notes. At least I can't hear.
Okay, so great. By close to the end, I hope there were some people who were starting to recognize the song, even if not all the notes were playing. So even though close to the end, there's still a lot of gaps in the notes on the piano, it's still amazing that your brain can fill in the holes and still tell you what you're listening to. If you didn't recognize the song, you could still probably follow along with the beat.
Katie?
Yeah.
Could you play it again? I don't think I certainly couldn't hear anything of it.
Oh, okay. I thought I was playing it through my. I turned my sound off because I thought I played. Share computer sound. Okay, so it must not have shared my. Oh, okay. I see what happened. I have to install something. I'm just gonna. I'll play it again. Sorry about that. I thought you guys were hearing it.
That's okay. I just wanted to make sure our audience got the full experience.
No, thank you for telling me you didn't hear it. I'm gonna play it one more time.
Okay.
Do you hear it now?
Yes. Yes.
Great. Cool. So sorry about that. I thought you guys heard it the first time. Thanks, Cameron, for letting me know.
Yeah, no problem. It worked that time. That was awesome.
Great. Yeah. So as I was saying, like close to the end, there were still a lot of missing notes, but maybe I'm hoping some of you were able to still kind of identify what the song was, or just if you didn't know, still be able to follow along with the beat. So our brain in that case is filling in the holes of the notes and still trying to tell you what you're listening to. And so this is very similar to how the imaging algorithms work that we develop for the Event Horizon Telescope. Using the sparse data we collect, the imaging algorithms we develop fill in the missing notes to try to reconstruct basically the underlying black hole image. And so in the case with identifying the broken piano keys, there's still an infinite number of ways that those broken keys could have been played. Someone could have just been banging on them, right? But there's a more likely option. And so similarly, there's an infinite number of possible images in the black hole imaging problem that fit the data we measure. But just like our brain preferred some melodies over others, in the black hole imaging of the images that are consistent with the measured data, there are some images that are more likely than others. And thus our goal becomes to find an image that doesn't just fit the data, but is likely under some sort of model of likely images. And so you can see here that maybe we think this image on the left just looks really messy, and we believe the image should be smooth or compact, and that makes the image on the right maybe more probable. And so using this idea, we developed a number of different kinds of algorithms that would recover an image from some input data. But you might say like, hey, you've never seen a black hole before, so maybe it is supposed to look crazy. And you're right, we needed to be really careful with the assumptions we made. For instance, we didn't want to accidentally have a preference for ring images and then be really excited that we recovered a ring back in the end. So we had to be very careful when making images. And so the big question we faced in dealing with the black hole data is not just how to make an image, but also how do we verify what we're reconstructing with our imaging algorithms is real? And we tackled this through a multi-step process. The first step actually began years before we even collected the data of the black hole. And that was to run synthetic data tests. And we did this through what we call the Event Horizon Telescope Imaging Challenges, where we'd have a team of people simulate realistic data sets that were then distributed so that anyone could try to make an image from them. And then these data sets were distributed without any information about what the true image was used to generate the data. And then different groups using different imaging methods would then reconstruct their images, making their best guess at what the picture should be. And then from this, we would pass the submitted images off to another group, a few astrophysics experts that we'd recruit to try to predict what the underlying structure of that image was, of the true images. And this is essentially what we were going to have to do when we were working with the real data. We weren't going to know what the true source looks like. And so we'd have to use these imaging algorithms we developed to try to make our best guess at the true underlying structure. However, unlike in the real data case, because the data is simulated, at the end of it all, we could compare to the true image and see how well we matched it. And so I want to show you a few examples of things we've seen in these imaging challenges. So here is one example. The true image used to generate the data is on the top, and on the bottom shows different images submitted to the challenges that were done by different people. And although each image was reconstructed independently from one another, you see that a lot of them, they have a lot of consistent structure with a bright spot more on the left side. But there is also a lot of differences between them. There's different kinds of wispy structures that are coming off. And so by looking at what is similar and different across them, we can try to gain confidence in certain features and reject others as artifacts. So this is one thing we learned from the challenges. Another is that we tried to test ourselves. So we, for instance, I snuck in some crazy kind of images. So here is another one of the challenges we had. And the reason I like to show this is because, clearly no one is expecting that a snowman was going to be in the center of the galaxy. And obviously our imaging methods aren't designed for that either. But despite that, we're still able to get surprising structure, giving us confidence that if there was something crazy and different than what we'd expect in the black hole image, then we would be able to recover it with our algorithms. So based upon these synthetic data tests, we developed how we were going to go and approach the actual M87 data. So we wanted to avoid shared human bias like we had done in the imaging challenges to assess common features among independent reconstructions. And so to tackle this, we split about 40 people who worked on imaging. Either they developed methods or they were just very knowledgeable at using methods, very experienced users. We split them into 4 teams that span the Earth. And actually, when we received data of the M87 black hole, we said, okay, split into your 4 teams and do not talk to each other at all during the imaging process. And we worked in isolation, trying to make the best image from the data for 7 weeks, actually. And so this is what we produced on team 1, the team I was in at the end of the first day that we worked on the data. And although we were absolutely thrilled to see this image, it was so amazing to see it, we wanted to be very cautious. We still weren't 100% sure. And we wanted to make sure that we were understanding the data correctly and not biasing it too much towards this structure that we were seeing. So our team continued to work on making an image from the data for 7 weeks. And then after 7 weeks, we all gathered together and we revealed the images we were getting to one another. And this is what we saw. So this was really amazing. Although every picture was different, just as they were like in the imaging challenges, they all reconstructed the same basic structure. This ring of roughly 40 micro arc seconds that's brighter on the bottom than the top. And so seeing these images was one of the happiest moments that I and many others had in the collaboration because it brought a whole other level of confidence to our results. We found the same structure no matter who was reconstructing the image or what method we were using. And without having done this test and having different people reconstruct with different methods, we would have never achieved the same level of confidence in our results. That being said, that doesn't mean that just because we had avoided shared human bias, we had avoided human bias altogether. And so we wanted to make sure that we weren't imposing some human bias that we wanted to see this ring. And so we spent the next couple months essentially trying to break our images. And that led to the next step, where we tried to develop methods to automatically reconstruct images while trying to remove humans from the loop as much as possible. And to do this, we coded up 3 different imaging pipelines, 3 different kinds of generic algorithms. And these algorithms all have their individual knobs on them, the hyperparameters that are usually tuned by a human user when you're doing the imaging. By the way, you can download these scripts, these algorithms along with the data online, so you can try to make your own imaging algorithms or play around with the ones that we've published. But anyway, okay, they all have their own hyperparameters. And instead of having a human tune them, we instead wanted the computer to search for the best set of knob settings to recover different kinds of source structures. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center. And then we asked the computer to find the best parameters to recover this disk shape. And then when transferring these exact parameters onto the M87 data, we found that although we had tried our hardest to find parameters that would best recover a disk with no hole in the center, our methods required us to put that hole there for the M87 data. And by doing this simple training and testing procedure on many different types of underlying sources and finding all the sets of parameters that gave reasonable results, we saw that our methods predominantly always preferred this ring shape. And that was true no matter the day we observed M87 on, or the imaging code that we use to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed the rest of the world last April, this ring of light surrounding a black hole, roughly 40 microarcseconds in size, brighter on the bottom than the top. Okay, and so we've recovered at this point, in my opinion, this beautiful image of the light circling around the black hole. But one question you might have is, what did we learn from it? What science have we learned from this picture? And so one question I get a lot is, did we prove Einstein was right? And well, I like to say the short answer is no, we didn't, but we also didn't prove he was wrong, which is a pretty big deal too. And so I want to just kind of talk you through a little bit of how we can use this image to tell ourselves about gravity and about black holes. Okay, so for any size object, you can calculate its escape velocity, the critical velocity necessary for an object to launch off to infinity, the square root of 2gm over r. You might remember it a little bit from your high school physics. And notice this doesn't depend at all on the mass of the object you're launching, just what you're launching off of it. And so what happens if the escape velocity is more than the speed of light? Well, then not even light can escape, and so you get this dark star or black hole. And so if you take a fixed size mass from this equation, you can calculate the particular size you need to compress it down to in order to get a black hole. And this critical radius is called the Schwarzschild radius. But actually, what generally we expect to see is not this event horizon itself, not this itself, but actually the point at which photons are orbiting around the black hole. So they will orbit maybe a couple times before flinging off to us and coming to us for us to image. But actually, not even that ring size is what we expect to see. Due to the immense gravity around the black hole, this photon orbit is actually lensed out and becomes bigger. So for a non-spinning black hole, the diameter is about 5.2 times the Schwarzschild radius. And if the black hole is spinning, it appears smaller, so it gets pulled in a little bit. And so this is the range of diameters between 4.8 and 5.2 times the Schwarzschild radius, which is the range that we'd expect if a black hole was obeying canonical general relativity. And notice that this is directly depending on the mass of the black hole, that M parameter. So for a smaller mass black hole, this ring becomes smaller. And that's interesting because actually from past measurements of M87's mass before the Event Horizon Telescope took the picture, it was really unclear what the mass of this black hole was. Gas dynamics pointed us to around 3.5 billion solar masses, but stellar dynamics pointed us more towards 6.5 billions. And stellar dynamics really provided an upper limit because there couldn't have been more mass in the black hole than was within the stellar orbits. And so we wouldn't expect a ring any bigger than this yellow one. But then we could ask ourselves, okay, how do we turn this into a test of black holes in general? Well, we can look at other unusual exotic objects. For instance, wormholes also produce a shadow feature. However, wormholes have a smaller shadow than black holes. And naked singularities or super splitting black holes also produce shadows, but they would even be much smaller than that. And when you lay the Event Horizon Telescope image on top of them all, you kind of instantly rule out all these other exotic possibilities, and you're left with a ring that matches nearly perfectly with the stellar dynamical measurement of the black hole mass of around 6.5 billion solar masses, if the black holes obeying canonical general relativity. So this is just one of the many things we can learn about black holes and gravity by studying this image. But perhaps the most amazing thing we see is that by comparing this picture to simulations scientists have made for years, we find that the image we've taken is actually amazingly consistent with a number of these predictions. However, you might have noticed the simulation I just showed you, it's moving. So is our recovered image of M87 also moving? And in fact, it turns out that it is. So another interesting thing is we imaged the M87 black hole over the span of a week, 4 different days, 2 days closer to the beginning of the week and 2 days closer to the end. And so we independently imaged each of these, and we can string them together and play them as a movie. And so I'll play it for you here, and you'll see that there's some evolution. So it's really hard to see it, so I'm going to play it again. You're going to notice the brightness moves more from the left-hand side, more to the bottom. There we go. So we don't know exactly what this evolution is caused by, whether it's material rotating or just filaments getting brighter and dimmer. But what we are sure of is that that black hole is evolving. And that's because it appears in the raw measurements we take. And actually getting a hold of a black hole's time variability is quite important for a number of reasons. It not only gives us a window to the dynamics of what's going on around a black hole, and hopefully an understanding of, for instance, how these powerful jets are forming, but it also helps us in mapping the space-time of the black hole and constraining our prediction of general relativity even further. But actually, the M87 is not the only black hole that we're interested in imaging to get a handle on the question of time variability. In fact, in the heart of our own Milky Way galaxy, 26,000 light years away from us, there's this cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the path of this cluster of stars for decades. And these stars seem to orbit like an invisible object. And by tracking the motions of the stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is a supermassive black hole. In fact, this discovery led to the Nobel Prize in Physics just a few weeks ago for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius A star, or Sag star for short. So as awesome as M87 has been, Sagittarius A star might be able to help us better understand these questions. Sag star is teeny tiny compared to M87, only a measly 4 million solar masses. But because it's so much closer to us, it actually appears about the same size on the sky. So because of that, we should be able to image it with the Event Horizon Telescope. But since it is so small, that means that the gas can orbit around it much more quickly. So whereas it takes 4 to 30 days for the gas to make a complete orbit around M87, for Sag star, gas can make a full orbit every 4 to 30 minutes. And so we'd love to be able to image the time variations in Sag star. And to do that, we've been developing methods to try to recover not just static images from the data, but actually full movies. But if you thought recovering the static image was a hard problem, this is orders of magnitude more challenging. We have the same amount of data, but now we have to solve for the pixels in a full movie rather than just a single frame. And so as important as it is to continue pushing the algorithmic approaches to squeeze more out of the data we've already collected, it's also important to realize that to extract more science, we have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And so to help us take better pictures in the future, we're trying to design a next generation array, which expands our network of telescopes from the 6 different locations on the Earth we observed within 2017. And so we've already begun building out our array to get more data, adding telescopes in Greenland, France, Arizona. And the one I'm most excited about is we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory. So Caltech is becoming part of the EHT telescope, which I'm thrilled about. But imagine what we could do if we added 10 more. Well, maybe we could actually make that video of the gas falling into the black hole in the center of our galaxy. And being able to do this would be this huge scientific goldmine, as I said. But before we just plop down a bunch of telescopes, we have to be really careful. Building new telescopes is really expensive, at least millions, but often tens of millions of dollars. And so we should try to optimize to find the locations that are going to give us the biggest bang for our buck. And so by developing new machine learning approaches that optimize the future telescope array, we're starting to understand where we may be wanting to place the next ground-based telescopes to reveal more of the unseen. And I'm also excited that we soon may be able to apply these methods to a variety of other scenarios, including even the optimal placement of telescopes in space, which was actually a topic of a Keck Institute for Space Studies workshop with Caltech and JPL this past year. And so hopefully by jointly improving our telescope array and our reconstruction methods and doing them simultaneously, we may soon be able to see even more. And so, really we're just at the beginning. And now that we have this extreme laboratory of gravity that we can test, we're thinking of all the ways that we can improve our instruments and algorithms, improve them jointly and learn even more. But I just want to mention that none of this work would have been possible without the amazing set of interdisciplinary collaborators that I have the opportunity to work with on a daily basis. And so I'm so lucky to have the opportunity to work with this talented group who continues to push science, the boundaries of science every day. And so going forward, I hope you have a chance to work on some amazing problems, work with a great set of collaborators and do something exciting and that you thought also wasn't possible. So thank you. Happy to take questions.
Excellent. Thank you, Katie. That was great. Okay, yeah, we've had some, let's see. We've had some wonderful questions from the audience. Keep asking them, everyone. Our Q&A will, as I mentioned before, our Q&A will consist of a whole panel of us, being comprised of Katie, myself, and Nitika and Jordan. Do you guys want to unmute and come on screen? Oh, great. Okay, awesome. So just really quickly before we get into addressing the question, I just want to have you guys hopefully know after the last 30 minutes what Katie works on, all the awesome topics that Katie works on. So now our other panelists that'll be addressing questions as well. I'll just have everyone give a one introduction to who they are and what sort of science they work on. So Nitika, would you like to go?
Yeah, sure, Cameron. So hello, everybody. My name is Nitika. I'm a third-year graduate student in the Caltech Astronomy Department, and I work in the radio astronomy group. And my current research project is I'm commissioning a new telescope at the Owens Valley Radio Observatory called Sprite.
Awesome. Is it going to be related at all to the EHT? This is a different telescope, presumably.
So Sprite will be separate from the EHT, but so Sprite is basically, there's these old antennas left over at OVRO from a previous array called Karma. And so there's a bunch of these 10-meter antennas, and we're using some of them for Sprite, but one of them is going to become the new EHT antenna.
Yes, and Nitika and I will hopefully get to work together on this a little bit. I'm excited.
Yeah, that's awesome.
Yeah.
Okay, Jordan, would you like to introduce yourself?
Sure, yeah. I'm Jordan. I'm a postdoc at Caltech in Tapir. I specialize in black hole research, and I've been working with the Simulating Extreme Spacetimes collaboration to develop a new code base that targets good simulations of binary mergers. So looking at collisions of binary black holes that produce gravitational waves or binary neutron stars that produce both gravitational waves and electromagnetic counterparts, and getting really precise simulations of these extreme systems.
Awesome. And you're part of the LIGO science collaboration, correct?
That's correct. That is also true.
Okay, sweet. And yeah, I'm Cameron. I am a postdoc in the department as well. I do computational modeling of how galaxies form and evolve over the age of the universe to make the beautiful things that we exist in and the things that we see today, consisting of lots of stars and black holes, like what Kim was talking about, these supermassive black holes like Sagittarius A star, or the black hole in the center of M87, and trying to self-consistently model that so we can understand how these things change over time. So, okay. Let's delve into some questions from the audience. So yeah, feel free to keep asking questions in the YouTube chat and we will try and get to them. Let's see. Here's a good one, kind of a general question for Katie. Can we use space telescopes for interferometry? Yeah, can we use space telescopes combined with the ground-based?
Yes. Good question. So I kind of hinted to this in one of my last slides that there is a possibility of going to space. So as I talked about near the beginning, we're limited in the resolution that we can see by the Earth's diameter. So we can only see at a very particular kind of range of wavelengths, and that we can kind of see through all the other gas and dust to get that ring of light. And so that is we're limited there. So to get higher resolution, you have to go to longer baselines. Basically, the farther the distance between the telescopes, the higher spatial frequencies that you, the finer detail that you probe in the image. So to get more resolution, we have to go to bigger baselines. And so then the natural question is, well, can we go to space? And so theoretically, yes, I think, but it costs a lot of money and there's a lot of technology that would have to be developed for it. So one is that the Event Horizon Telescope itself is kind of pushing the boundaries of these long baseline interferometry, and a lot of instrument development has to be done even for the Event Horizon Telescope to have even worked on the ground. And actually, though, the Event Horizon Telescope compared to many kinds of science experiments was fairly cheap. It was under $100 million. It's a little hard to put an exact price tag on it, but the reason it's so cheap is because it was able to leverage other telescopes on the ground and just put specialized equipment in them in order to make them work together. Going to space, well, you're going to have to build a very special telescope, but also going to space is very expensive. So whereas it was like under $100 million to kind of build the telescope on Earth we have now, the array of them, even putting one telescope in space, people at JPL predict it would be at least $500 million. So it's a big increase in the price tag of the project. And so you have to just prove that you have a science case that's worthy of spending that kind of money. And there are reasons that we'd want to do it. You can go and see more black holes at higher, you can see more black holes that we can't see from Earth potentially. Also, there's a chance of getting more information about time variability. And there's a lot of reasons that we would want to go to space, and we're always pushing the boundaries. So that's one thing. But as I said, lots of technical development that would have to go into making it possible.
One thing that I wanted to add on it too, maybe not from the radio perspective, but maybe 15 years ago, there was a planned optical interferometer that existed in the visible wavelengths that was meant to go into space, called the Space Interferometry Mission, SIM. But rather than it was like two telescopes that were connected by a crossbeam that was like, I don't know, 5 meters wide or something like that. But it ended up being really expensive, so they didn't end up doing it.
That's really cool. I actually didn't know about that one. They do interferometry, radio interferometry from space. So there's one called Radio Astron that we actually analyze the data from, right? Sorry, not right, but there's one that we analyze the data from that connects to a ground-based telescope. This goes out, it has an orbit, elliptical orbit that goes out almost to the moon. So it's which is I think 28 Earth diameters or something very large baselines that you have, but it works at longer wavelengths. So going down to around a 1 millimeter wavelength or optical, like you had talked about, is really challenging, right? You have to be very precise in your alignment of the signals and time, and so you don't have any of that slop, room that you might have in longer wavelengths. So yeah, I think the challenge is really going to that short baseline, the short wavelength.
Yeah, the short wavelength, I think the crossbeam had to be precise to the picometer distant baseline distance, which is just ridiculous. That's, 10 billionth times smaller than a centimeter.
Yeah, and I'm guessing that even then they would have to do additional processing to get even finer than that.
Exactly. So a related question, actually, I have a really quick question that's related to all this. With the Event Horizon Telescope having the many different dishes that are on the surface and it's rotating, but do you also get to account for any kind of the orbit of the Earth around the sun? Obviously traces out a much larger, but it seems like maybe your observing period is so short that you don't get a lot of that orbital drift that could increase your baseline.
Yeah, it's a really good question. The problem is we have to be measuring the signal simultaneously. So it's not like coherent in time. So you have to really be precise in time to form a measurement from a baseline. So it's not like we can observe in the spring and then observe in the fall and then use that as a big baseline. I wish.
Okay, that makes sense then. Okay, thank you. Okay, speaking of space telescopes, is it better to have a telescope flying in orbit or a telescope on the moon is better?
Also a really good question. So this is I don't know actually. So I'll tell you the pros and cons of the different orbits in a nutshell, hopefully. So this is part of the thing we're studying with JPL of what we want. And it really depends on the science case. So if you have one telescope that's on the moon, that's a really long baseline, right? So you're probing, you're getting very fine detail, but it's like if you only saw the edges of the image and you couldn't see anything but like noise in an image then, right? So if you know exactly what you're looking for, let's say we know that we're looking for a ring and we just want to model fit what's the diameter of that ring, then having a very long baseline would give us more would give us like higher resolution information about that, but we probably wouldn't be able to make a picture because we don't have all the information. There's so much missing information there that we can't tie it to its it's just like recovering a picture just with the edges, but it's worse than that. But there is a reason that you'd want to do that. On the other hand, you can put a telescope in a lower Earth orbit. It's rotating around the Earth really quickly, and in that case, a low Earth orbit allows us to fill out that measurement space really fast because you have this telescope moving around really quickly, faster than the Earth is rotating. And that allows you to, for instance, do better video reconstruction. You can get lots of measurements very fast over the entire space. So it kind of depends on, do you want more resolution but not to make a picture, or do you want to not higher resolution but get better temporal resolution?
Yeah, I just want to add on top of that this is a bit tangential. It's not related to the AHT, but if people are interested in the concept of telescopes on the moon, there is another professor in the Caltech astronomy department named Greg Hallinan, and he is currently working on a low frequency array called FarSide that's going to be on the far side of the moon. So for context, the EHT observes at a very high frequency, like 230 gigahertz, but Greg's project is interested in like 10 megahertz observations to probe magnetic fields around stars and planets. But that's a super cool project too, and I definitely encourage people to go look that up.
Yeah, thank you. That's such a great point. And actually, I think Greg gave a talk that I think is online, I'm guessing, a couple weeks ago, a KISS talk. It was excellent, really good. So I recommend watching that project.
Yeah, me too. That was a really awesome talk.
I'll have to check it out. I don't think I caught it, but Greg is a great speaker. Okay. This is a question, I guess, for both Jordan as well as Katie. Can you see anything behind the black hole? If yes, then how? So,
Jordan, do you want to go first, or?
You go ahead.
Okay. So we have this we have this really small field of view. So we really are seeing just kind of the immediate region around the black hole. We can't really see much around it. In fact, I talked about this like booming jet that is coming off of it. that you can, yeah, that's the size of the entire galaxy, really. And we can't even see it in our pictures. So we know it is there, but because we don't have that, well, first of all, we're zoomed in. We only are probing very certain kind of spatial scales of our image. We kind of miss it completely. We're invisible to it. So it's almost like you're looking at a bird flying in the sky and it's moving over a cloud, but you've zoomed in so much that you can't see the cloud and it just looks like it's going over flat sky or something. So one reason that we do want to expand the Event Horizon Telescope is so we can connect it to the other structures that's around it. But even then, we're not going to be able to see structures in front or behind it because it's all kind of blurred out. Yeah.
So Katie gave the practical answer for what we can actually do, and I have the sort of theoretician side of it of let's say we were in a spacecraft sufficiently close to a black hole, then what would we see? And the answer is we definitely see all of the things behind it, but it's not near where we might expect them to be. It's entirely lensed. If you remember this great animation in Katie's slides, you do actually see things that are physically on the opposite side of the black hole from where you are, but then it forms this ring around the black hole in terms of where you would see it on the camera.
Yeah, such a good point.
So we can see that stuff, but we have to reconstruct what that means in actual like space because it's all warped by the presence of the black hole.
Exactly.
Okay. So how close do we have to be? I mean, I know we have examples of gravitational lenses from massive objects distant from us, like other galaxies or clusters of galaxies. For instance, do you have a good idea? And I don't. Do you have a good idea on how close we would have to be, for instance, to the supermassive black hole in our galaxy to be able to see what's, I mean, I guess the geometry, it's going to depend on how close it is behind it to be able to see that stuff. I don't know. I'm just trying to, do we see any gravitational lensing effects from Sagittarius A star? I don't know of any, but it seems like maybe we're too close for it or it's not massive enough.
Well, I'm not sure. So, I mean, I do know that there are these studies of tracking stars that swing very close to Sagittarius A star.
Sure.
And I'm trying to recall, and I don't have the right answer to this, but it could be studied exactly to say how much smearing there is in the image of those stars as they pass sort of close to where we would imagine Sagittarius A star to be kind of between us and them.
Right. Okay, cool. Thanks, guys. That was good. Let's see. What's another good question here? Lots of good questions. Probably the most good questions we've had from a talk so far. So this is great. Let's see. Oh, here's just kind of a general question for Katie. How much of your work is computer science versus physics?
Yeah, good question. So actually, I don't just, as I kind of hinted to in the middle of the talk, I don't just work on astronomy problems. I like working on a variety of different kinds of imaging problems. So for instance, people in my group, some are working on medical imaging, some on seismic imaging, different applications to some on climate studies with the cloud imaging and different things like this. And they all kind of have a very similar kind of methodology to them. This idea of merging algorithms and sensors. And how do you do that in an optimal way and understand, and in doing that, you really have to, I like to understand the physics behind the problems of how are the measurements being acquired and what kinds of noise that come into them and how are they corrupted and stuff. And that's really important to understand because when you're solving an inverse problem, you have some like clues, right? And your goal is to find the thing that is causing those clues, and the physics connects those two. But a lot of times there's also a lot of missing information, as I said, and so we have to fill in the gaps of knowledge. And so that's what kind of flavor of all these projects. They're all different applications, but they all really have the same kind of basic structure of how you go about solving them. And so I don't know if I'd say computer science, how much of them are computer science, because I think computer science is just like everything these days. Everyone in astronomy is using a computer and coding and stuff like, and that's just such an essential part of so many areas. But what thing that is particular to my group is in developing algorithms and using computational tools in order to extract more from the data. So doing kind of data science, data analysis. And so I myself am not a physicist. I have or an astronomer or anything. Everything I've learned about black holes is by talking with my amazing colleagues and learning it from them, which is fun. And I love working on these projects because it gives me an excuse to learn about a different field, really. But yeah, most of my day is I was working on algorithms that to extract more from the data. But part of that is understanding the physics. That is an essential ingredient. And you can't just like come in, you can't come up with a generic method and like throw it over the fence and hope it works. You really have to understand the intricacies of the problem and design algorithms to solve those problems, to get it to work.
That's awesome. That's cool. Okay, this is a question.
I think Nitika, isn't your background not in astronomy as well? I don't know if that's right. My background was also in mechanical engineering, and I took some astronomy classes when I was an undergrad, but I feel like 90% of the astronomy I've learned in the last 2 years in grad school. So it's been a process for sure.
Do you find yourself using a lot of the same ideas that you learned in your undergrad, or how overlapping?
Yeah, I do. I started my career thinking I wanted to be an engineer. And then when I got interested in astronomy, what I decided was I wanted to see what was at the intersection of astronomy and engineering. And I ended up coming to Caltech because this is one of the best places in the country and probably the world to do like instrumentation and telescope design. So that's mainly what my research has been focused on, is learning more about the process of how telescopes are designed and the way that collaborations work and the process in which they're commissioned. So yeah, kind of similar to Katie, a lot of the astronomy I've learned has been like consolidated in this time.
On the job work. This is too. I studied computer science as an undergraduate.
Oh, really?
And switched to doing more astronomy and physics stuff. But what I'm doing most of the time now is all coding. I mean, it's hydrodynamical modeling, so it's all code for an application of a physical system.
Mm-hmm.
And I feel like to those children and parents and aspiring astronomers out there, I would encourage you to do a lot of background work in terms of learning coding and learning to use computers, because it seems like pretty much any quantitative science, you're going to be using a ton of computer work. So
becoming more and more of an essential tool.
Absolutely. Yeah, I know, Jordan, you spend all your time coding, right?
Effectively, yeah, that's true.
Yeah, so, okay. Here's a question we've had in a few different forms so far from the audience. So do you think in the future we'll do visible spectrum, visible light interferometry, kind of like we mentioned before, and get higher resolution images of a black hole, or are radio images a better choice? What's going to be, what's like the next frontier for these high resolution? Is it just filling in? Sorry, my internet keeps cutting out. I'm in a hotel in Arizona right now, so it's not great. But do you think it's better, like you were referring to fill in, to have higher baseline stuff to switch to a different part of the electromagnetic spectrum, or to fill in your footprint and have more things on the ground?
Yeah, so there is optical interferometry where you were working at optical visible wavelengths. Actually, like one of the most famous ones is with Mount Wilson, right? The optical interferometer, which is pretty exciting. I haven't gotten a chance to visit it yet. I tried, but the gates were closed, so I need to find another time to go. But anyway, yeah, so definitely you can do optical interferometry. The problem is in optical interferometry, you can't, so in the radio, in the wavelengths that we're working at, 230 gigahertz, which is around was 1.3 millimeter wavelength, we can still record the data, the light, we can kind of record it on those hard drives and then like fly it together. For optical, I don't think the data, you can record it, that you can't record it. And so everything has to be done in hardware, all right? So and so you can't have these baselines that are the size of the earth, right? Because you can't have optical fibers going that far and everything and doing the precise alignment and all of that. So you can't have, so we can't go to really, really high, that large of baselines. There is a infrared interferometry gravity, which works at the shorter wavelength than we use for the Event Horizon Telescope. And it has been, actually Reinhard Genzel is who won the Nobel Prize, is one of the main people who is a part of this gravity collaboration. And they actually been able to track, using this interferometer, been able to track the kind of flares or different kind of hot spots moving around the Sagittarius A star black hole. And so that is they're not doing imaging, but they're tracking features to actually higher resolution or about the same resolution as the EHT can track. So it doesn't make an image, but it has a very precise location of where these kind of features are moving in the image. So that's one thing. The EHT is limited in the wavelength it can use, at least on Earth. We can really go between 0.8 millimeters and 1.3 millimeter wavelengths. That's limited due to like the atmosphere and also the gas that kind of shrouds the black hole. It's not optically thin enough for us to see that ring of light when we go to too long of wavelengths. And so we kind of have this like sweet spot of around a 1 millimeter wavelength that we can do imaging with. Yeah. I don't know if Nitika or
Excellent.
Jordan have any additional, or Cameron, if you have any additional information to add on it.
I think that was a great summary of that. Yeah.
That was good. Let's see. Can you draw any confirming conclusions about the existence of Hawking radiation from the EHT results? That's for the audience that's not familiar with Hawking radiation, it's named after Stephen Hawking because he was the one to predict it. And it's essentially that black holes slowly evaporate much of their mass, but it's very dependent on the mass of the object. And for large massive black holes like these, like M87 or whatnot, it would take many times the age of the universe to fully evaporate. But do we have any insight into that from the results that you guys were able to get, or that you may be able to get in the distant future?
So definitely not from the results that we got. And as you said, for very massive black holes, they evaporate very slowly, as you said, like some insane amount of time. So I think it's even harder to detect would be even harder to detect anything on a supermassive black hole that is not evaporating very fast. But I don't think that, I think it's such a, yeah, I don't think that there's any kind of hope of that with the Event Horizon Telescope, but I don't know if Jordan, if you have any insights into this.
My only comment is that if we're going to see Hawking radiation at all, I think the likely candidate would be any smaller black holes, right? Because this is exactly what Katie and Cameron were saying, is that the extremely large black holes, they're not only do they evaporate more slowly because there's more mass to get rid of, their temperature is also far lower, their sort of effective temperature of the radiation. So it's dimmer as well. If you want to play around with the idea of primordial black holes that might be smaller, not caused by a stellar collapse scenario, then you might be able to make a convincing argument that there could exist black holes that are small enough to be bright enough to actually be detected, although I think that chance is extremely slim as well.
Cool. Question that was just asked, why, this is for Katie, why is the light brighter at the near side of the black hole image?
Yeah, good question. So the black holes, actually, so you have, when you have a black hole, you have this accretion disk of gas that is kind of moving around the black hole. And it's actually kind of like a puffy donut for us. But actually, because the gas is moving around so quickly, it's so close to the speed of light, it's Doppler boosted. So when it's moving towards us, it's brighter. And when it's moving away from us, it's dimmer. And so actually, if you were looking face on at the black hole, it would look all the same brightness. But because it's tilted a little bit away from us, that means we're looking at it a little bit at an angle. That means some of the gas is moving towards us faster than the other. And so you have the gas that's moving around, it's lensed around it into this ring, but some is moving towards us and some is moving away from us. And so what that tells us is, because we know the black hole is probably pointed at, the jets are pointed about a 20-degree angle, 17, 20-degree angle. You have the accretion disk, we think is like this, is a little 20 degrees pointed away from us. And so that means that on the bottom of the disk, it's moving towards us. And on the top, it's moving away from us. So using your right-hand rule, you can see that this is the black holes, the gas is spinning around it away from us, I guess. And so that's, yeah, that's why the bottom part is slightly brighter than the top part.
I see. And related to that is the rotation of the gas in the accretion disk. Is that the same rotation direction as the spin for the Kerr black hole, or do we not know? That's just something I'm ignorant of.
Yeah, it's not necessarily, but I think it's much more likely that it is. So you can find like parameter settings so that it's spinning in the opposite direction, but there were less. So there was, wasn't deep in this analysis, but you can read it in the papers of like, what is the more likely parameter settings of the black hole based upon the observations of the Event Horizon Telescope and other observations at other wavelengths. And I think that you could find that as an option, but it was much more unlikely.
I see. Okay. Interesting. And there was a question related to all of this and related to spin that perhaps is a bit of a philosophical question, but I know perhaps many of the audience members know this. There's a saying that black holes have no hair, which just basically means that for a black hole, there are only three quantities that really matter, that we can really measure, and that's the mass of it, how much stuff is in there, its spin, and then its charge. And we have a couple of questions that are related to that, but what does it mean for it to have spin? Because ultimately we believe that it's an infinitesimal point. So is it some sort of intrinsic spin like electrons have and subatomic particles have that aren't actually spinning? Or is it actually that the mass inside the event horizon is somehow spinning, or related to what we were just talking about with the gas that's, I guess it's probably related to that. Like the gas comes in with a spin, and because of conservation of angular momentum, it has to go into the black hole. But I don't know. Do you guys, black hole specialists, have anything to reveal the secrets?
I think what you said last is, I think the most, what people think is causing the spin, but I don't know actually beyond that what it means to be spinning. So I don't know if someone else has a more theoretical.
So there's a couple of comments. First, Kerr black holes don't actually have a point-like singularity. They have a ring singularity. So
Okay.
there is a slight difference there associated with this parameter that describes the spin. I mean, for observers outside the event horizon, what the singularity looks like doesn't make a big difference. But I think the correct description, both for the spin and for the charge, is exactly what you alluded to towards the end of the question, Cameron, is that we shouldn't think of these things as sort of intrinsic properties of how matter moves or what matter is, but instead entirely in terms of conservation laws. So if you have angular momentum in your star, for instance, that forms a black hole, if you have angular momentum in the matter that falls into the black hole has angular momentum associated with it, primarily because the black hole, most of the black hole, what we think of it, isn't really the matter of it. It's it's what's known as a vacuum solution. And that vacuum solution is defined effectively by the amount of angular momentum it has. And then that influences the effect that it has on the space-time around it. And I think the same explanation is valuable to consider for electromagnetic charge, because again, it's about conservation. You have some electromagnetic charge and you throw it into a black hole, and you have to conclude that the electromagnetic charge couldn't have been destroyed by that. So it has to have the Coulomb field associated with the charge that you started with.
Is it possible to, I realize that based on what Katie was showing, that and based on the stuff that you do with the waveforms that get predicted for gravitational wave mergers, or mergers and gravitational wave outputs, that the spin of the black hole will show up in those waveforms or show up in the predictions of the image. Will the charge of the black hole also influence the output image or the output of the waveform?
So Jordan, tell me if I'm wrong, but I've been told that astrophysical black holes do not have charge because they're usually neutralized. So that really only the spin and mass are relevant for astrophysical black holes.
Yeah, so some gravitational wave theorists will investigate charged black holes primarily because it's sort of an interesting toy problem, but it's not really explored for modeling purposes because it's exactly as Katie says. We don't expect there to be any astrophysically relevant quantity of charge that accumulates.
Just because the stuff that's going into it is probably net charge of 0. And so
right, or extremely close, right? Yeah.
Okay. But if you had like an electron, a white dwarf that fell in that was all, well, I guess even those. If you had something that had a massive electric charge, would it influence the waveform that you got out from two merging like negative charged objects?
Well, did we lose
Sorry, I
camera?
cut out.
Okay.
Sorry about
can I first answer the question of what happens with the spin? Because that's it. I don't know the answer for the charge, but I know for the spin, I guess, case. So at least for the black hole shadow stuff. So it would be cool to hear what Jordan has to say about the LIGO. But for the black hole shadow, we do expect to see the spin and the mass of the black hole has an imprint on that, what that photon orbit, the shape of that photon orbit is. The mass has the biggest effect. So it kind of determines the size of it. And the spin does have effect, though. It kind of squishes one side, depending on what your orientation is to the black hole, what viewing angle you're seeing it at. But the problem is that the spin is only going to cause a change of about plus or minus 4% to that shadow size. So with the resolution that we currently have for the Event Horizon Telescope, it's our resolution that we quote is higher, it's larger by resolution. You want small resolution here. So the resolution that we quote is bigger than the resolution we need in order to really see the effects of spin. So you can make some kind of constraining arguments, but it's would be pretty hard to constrain spin in that way. And so one thing that we're doing is why we want to go to observing dynamics and watching the black hole evolving over time, is that gives us a different way of kind of measuring spin. The dynamics kind of tell us and how the gas is falling into the black hole is another way that we can recover the spin. And so if we have mass and spin, we know everything about what the environment should be like around the black hole, and that helps us in our quest of constraining GR more. So, but yeah, I don't know for LIGO, they might be more sensitive to that.
Yeah, and it's similar to what you were saying about things falling into the black hole, right? That as you track the orbit of objects near a spinning black hole, and correspondingly as you track the orbits between two spinning black holes, I've got my thumbs because this is how numerical relativists represent spin, except it's frustrating because we don't have two right hands. The spin affects the in spiral enormously. And it's one of the things that really expands the number of different things we have to model in order to give LIGO good predictions for what kind of systems they could see, what sort of waveforms they could see. And it changes everything from the precise form of the waveform to how quickly it inspirals, whether the black holes are co-rotating or counter-rotating, as well as even what happens to the system following the black hole merger. Because as some of my colleagues are investigating, there's this interesting effect that if the spins are sort of just right relative, the remnant black hole receives what is called a large kick, that as compared to the original center of mass motion of the system, it has preferentially emitted gravitational radiation in one direction rather than the other. And then the final black hole goes flying off at some enormous velocity compared to the original system.
Are you sensitive to the magnitude of the spin or just the direction of the spin? With the
magnitude is determinable as well. There's sort of a complicated surface in the LIGO papers that are published for the directions that are less well constrained by determining the waveform. In principle, if you know the waveform exactly, you know all of this spin parameters, but there are certain directions in the parameter space that are closer to degenerate.
Great discussions, guys. Great discussions.
You should also get like a fake thumb so you can do
That's right. Get on the other side.
The Halloween, now that you get the Halloween discounts.
So there have been a few questions about why Sagittarius. I know that the Event Horizon Telescope was both trying to look at the black hole in M87 as well as our own Sagittarius A star, but the Sagittarius A star data wasn't published. Why has it been harder to image? And are there any hopes for us to be able to, in the future, get a published image of it?
Yes,
oh, I cut out.
Yeah, no, I got
back.
the question. We're working hard on it right now. So we're still working on it. It's a lot. Sagittarius A star is more difficult for a number of reasons. Well, one is that we kind of got lucky with M87. We didn't know what the mass was. As I said, there was this factor of 2. So if it was the smaller mass on the smaller sides, then it would have been harder to image M87. So we kind of got lucky. It was on the bigger side. But for Sag A star, there's a lot of things that we knew we were going to have challenges with that was going to make it hard. We have a better idea of what the size of it was. So we weren't like M87, we didn't know the size necessarily, but for Sag A star, we know that we should be able to see it if it is a ring. But the challenge with Sag A star is, as I said, because it is a smaller black hole, the gas is spinning around it much more quickly. And so, as I said, the gas makes a complete orbit every 4 to 30 minutes. And that means that, remember, over the course of a night, we're collecting the data. So we have these different baselines, they're carving out these elliptical paths. So every measurement is coming from a different point in time. And so if these measurements, they're all coming from different snapshots of the black hole, right? They're not all, so we can't like throw them all into the pot and say, find the static image, the single image that fits them all. We really have to consider the fact that it's a movie and it's changing over that time. And so it's a lot harder for that reason. It's a lot harder for that reason. Another thing is, so that's, I think, the main issue with Sag A star. The other big issue is scattering. So there's interstellar medium between us and the black hole, and this scatters the wavelengths that we observe. It doesn't scatter it so badly so we should be able to see the structure of the black hole, but it's kind of like looking at the black hole through a frosted window. And so we have to kind of understand that scattering and remove it, because the scattering screen is actually moving itself. So there's 2 forms of evolution that are happening, and we have to disentangle them. So we're working on it, but it's yeah, it's just a lot more challenging for that reason. And as I said, we're also working on developing the next generation of the Event Horizon Telescope, which Nitika is also is being a part of. And that will be building out the telescope, building out that OVRO telescope and other telescopes around the world that we're currently designing what that would look like. And a part of that is being able to actually make a movie of the black hole. So what we might expect from the first Sagittarius star data is not being able to see that movie. We'll probably be doing some methods to mitigate the effects of the variability so that it doesn't hurt us in making a static image. But then later on, we'd like to actually be able to make a movie.
I see. And potentially, oh shoot, I'm frozen. Am I back? I'm back.
You're
Okay.
back, yeah.
Potentially Sagittarius A star would be a better choice for making a movie because you have a shorter baseline or a shorter time scale in between
Yeah.
the orbits and the motion.
Yeah, another thing is you could make a movie of M87, just image it over the course of a year. The problem is telescope time is very expensive, is very hard to get as well. Like whenever we observe, we actually have to propose for that time, and we don't always get it, in fact. And also to keep in mind that we have to observe with telescopes that are distributed around the globe. And especially when you have so few telescopes, weather and having one drop out due to weather is a big deal. So we actually find a time, usually we observe in late March, early April, which is the best time of year for all the telescopes we have. You know, I mean, it's not the best time for each one, but over all of them, it's the best time. And then we usually have a week. And during that week, we like trigger we usually have like 10 days, and during those 10 days we trigger like 5 of the days because the other days might have bad weather. So it's very hard to observe with a Earth-sized telescope. And so imaging M87 over the course of a year, there also has to be a lot of technical development that allows us to observe on demand without people at the sites, and then we'd have to be able to get that time to observe as well.
I see. A related question that I think would be well addressed by Nitika: what impacts will newer radio telescopes like the Square Kilometer Array have on future black hole imaging and research?
Yeah, that's a really good question. So the SKA, for people who aren't familiar, the Square Kilometer Array is going to be a new radio array in Australia. The thing with the SKA is that its observing frequencies are much, much lower than the EHT. So as previously mentioned, the Event Horizon Telescope observes at 230 gigahertz, whereas the SKA, for example, the highest frequency that it sees is only like 4 gigahertz. So that's one thing. The second thing with the SKA is that it's what we call a survey telescope. So in astronomy, you typically have missions that are in 2 classes. You have like pointing missions or you have survey missions. So the EHT would be what's considered a pointing mission because you have telescopes that you propose for time on, and if you get the time, they all stare at this one object for the amount of time that you've proposed for. A survey mission is not like that. It has its own observing plan. It'll measure like large portions of the sky at a time and will typically observe at the entire sky over the course of several months or years. And so that's the mode in which the SKA operates. But it does have goals for testing GR the same way that maybe the EHT would. So one of its interests is measuring emission from things like pulsars or binary pulsar systems, binary neutron star or black hole systems, and measuring radio emission from them. And aside from EHT related goals, it also has the goals of probing what the early universe looked like. And so they're all exciting missions, but they won't necessarily further the goals of the EHT directly.
Right. Okay. That makes sense. Yeah. It's always split between these big survey telescopes and the zoomed in like follow-up missions. Okay. Kind of a general question for all 4 of us, since we're all doing different computational work related to astronomy and physics. What programming languages do we use in our various work? Who wants to jump in? Oh, did I cut out? Gosh,
No,
this
no,
connection.
No, you're good.
people don't want to go first.
Because-
Jordan, you want to go first, or I can?
Sure. Yeah. Okay. So in the simulating extreme spacetimes collaboration, we use C++ to do all of the expensive computations that are farmed out to supercomputers. And we usually use Python as our go-to for performing data analysis on the outputs from the simulations.
Yeah, when I first joined the Event Horizon Telescope project and I was given some simulation code, it was in Fortran. And I thought this was a disaster. But luckily, a lot has been moved. And luckily, most of the work that I do is in Python now. Yeah, and when you have to use, C or C++ when I have to, but I'm lucky to mostly use Python. In grad school, I used a lot of MATLAB, but that's kind of gone out of fashion now. So yeah.
Yeah, I too only use Python for my research.
Yeah, I use Python for most of it. All of my analysis stuff on the simulations is in Python or Cython, which is a Pythonic language that can compile down to C code for really highly iterated stuff that you really need to make sure it's efficient. But the hydrodynamic codes that we build are C++, and then at the core of some of them, like Enzo, the code that I used through graduate school, the core is Fortran because it was written 30 years ago and is super, super efficient at what it does. And when you're running stuff millions and millions of times on a supercomputing cluster, you want it to be like at the peak of its game. So,
Yeah.
I will say though, it's not work that I do directly. Okay, I was just going to say this. I will say it's not work that I do directly because I'm not qualified to do it, but there are a lot of really talented engineers who work on radio telescopes that write code for GPUs and the GPU programming languages. And that's like a whole different class of research that some really talented people, especially at Caltech, work on for us.
Also FPGAs, right?
Yes, and FPGA programming. I mean, that's like people dedicate their careers to doing this type of programming just to make sure all of our computations run fast enough. And they're absolutely what make radio astronomy run at all.
what's FPGA?
So FPGA stands for Field Programmable Gate Array, and it's like my understanding of it. It's basically like programmable circuit hardware, and you configure it to make your computations run super fast.
So a lot of like radio astronomy, they program FPGAs because it's too expensive. And actually the FPGA, I don't know that much about them, but I think that they've become so good that it actually is not necessarily a big advantage to like actually having your circuit after you've designed it, actually have it manufactured. So it's kind of almost as good as that, and a cheaper alternative.
A grad school friend of mine would want me to make the joke that it's called field programmable gate array because it is programmed by the fields. It is technically true, but it's not why it's called that. It's programmable in the fields. You don't have to have specialized hardware.
I didn't even know what they meant by that. Yeah.
But of course, you move electrons around, so it's programmed by the field.
Good joke.
Here is a question for Katie. So when you were showing the various images of the black hole that the different teams had come up with, how did you account for all of those to go into your final image? Was it just averaging, or did you pick out the best method of the four, or how did you combine them?
Yeah, so actually, those images, those images made it into the final image we made. Basically, this initial stage of blind imaging was to make sure that we did not have shared human bias. So we didn't want to be influenced by our friends. You know, like I would see my friend making a beautiful picture on his computer and I'm like, I want that picture too. And, you know, forcing myself to kind of get the same picture. And so what we did is we separated ourselves to make sure we would avoid that shared human bias. But these were the very first images we ever made, which I think I really like telling that story because I think it's really cool how that happened. But, you know, later on there was refinement, a little bit of more refinement to the data to remove a few other calibration effects. And also we developed these pipelines that were then we could modify, like easily change these knobs, like what regularizer do we want to use, where a regularizer is like saying what preference do you have for the images, or how do you want to optimize the image, and different things like this. And then we ran these huge parameter surveys, so hundreds of thousands of different kind of parameter settings on these pipelines. And by testing how well they performed on synthetic data, we identified a set of parameters that we thought was good. And then based upon that, we got an image for every one of those pipelines and we averaged those images together. So actually none of those, the initial images made it into the final ones. The final one was done by doing synthetic data tests. And for instance, like I said, identifying what were the parameters that worked best to recover a disk, and then using kind of like those parameters to recover the M87 black hole. So it wasn't like us, we wanted to avoid our like tweaking the parameters to get a prettier picture, I guess. Yeah, and actually another interesting thing, I didn't have time to talk about it, but we actually are completely, we do not have information about the location of the picture of the black hole. So actually, when we reconstruct the picture, and it can appear anywhere on our screen, there's an offset in the location. And so to make the image, we aligned them. So we kind of found what the best alignment was, and then simply averaged. We actually came up with other algorithms to do more intelligent averaging and stuff, but we decided it wasn't necessary. Let's just do the simplest thing, and so that there can be no critiquing of us doing funny business to the images.
No funny business. Very important. Okay, question here for Jordan. Black holes have great mass and thus great gravitational force. Do black holes just consume other objects and grow their mass?
They do, though so they will, for instance, in these wonderful pictures that Katie and her collaborators have produced, the disk we see is known as an accretion disk, and this will slowly fall into the black hole, and at least part of that mass will contribute to growing the black hole slowly. Though with these supermassive black holes, it will be very slow as compared to their overall mass. What really produces a significant change in a black hole's mass is actually merging with another black hole in these black hole inspirals and collisions. And in those cases, it's sort of fairly efficient in terms of the component masses, that these are tens of solar mass black holes, often in the LIGO discoveries. And you end up with a final black hole that has lost only around, say, 3 solar masses, for instance, in one of the particularly loud LIGO events. Now, 3 solar masses converted to gravitational wave energy is enormous, but we end up with a bigger black hole afterwards. And then many scientists do these progenitor studies for, say, how did we get a black hole of one mass or another, and ask how likely it is that the black hole was formed by this sort of chain of mergers. Say we started at something that was a few solar masses that was plausible to come from a star. Did it merge several times to get these tens of solar mass black holes, or did it come from some other place?
Okay, cool. Thank you for that. So many questions. Gotta pick all the best ones. Sorry, guys. Just picking and choosing here related stuff. There was one. Oh, the black hole region. This is from a question we got from Facebook earlier. The black hole region must essentially be spherical. Although, Jordan, you were pointing out that the singularity in a spinning black hole is a ring, which is, I had no idea. That's pretty interesting. But the question is the accretion disk also, is it in an equatorial plane as it is always depicted in the diagrams, or is it not that shape? Like, what are the diagrams accurate in terms of showing it in like an accretion disk in a ring that's just kind of like planar?
So I think that it's mostly like I was saying, like this puffy donut. I think that's what people think it mostly is made up. And I think that there's going to be other stuff, but that's the primary thing. And then you have these jets coming off. So one question is like, is the light coming, is it bending from the jets or the accretion disk? And I think that is a valid question, but I think that this photon ring that you'd expect, the brightest area, it doesn't really matter if it is or from a close by jet or this puffy disk. But yeah, I think you have this puffy accretion disk and spinning around, and then you have the jets coming off. And if that puffy disk is like this, spinning this way, so you're edge on, you have the black hole here. When it's behind the black hole, it gets lensed around it. It bends around, and so you still have a ring of light. No matter which direction you're viewing it from, you're always going to get that ring of light, even if the disk is edge on to you. It's just the kind of what will change about it is a little bit how squished it is, and like based upon spin, and also it'll be brighter on one side than the other. It will be more extreme when you're edge on, that asymmetry that we see in the ring. I can't remember what the question was exactly, but maybe I answered it.
No, yeah. The question was kind of nebulous. And I guess so is the accretion disk, kind of. It's like a puffy donut. So that seems appropriate.
I think like this interstellar black hole, which is pretty accurate, except they ignored this Doppler.
From the interstellar film?
Yeah, the gargantua black hole from the interstellar. I think that is a thin disk black hole. So that's not the exact, so it has some differences there with what we kind of expect around M87.
Okay. So yours is puffier, like a puffier.
Some people should double check this, but this is what I understand.
Okay. Aside from Sagittarius A star and M87, what are other targets that the Event Horizon Telescope might look at in the future?
Yeah, so the two black holes, M87 and Sagittarius star, are the AHT's primary targets. And that's because those are the two black holes that we know of that we could see Event Horizon scale structure with an Earth-sized telescope. But we do look at other sources. So actually with the M87 image, we published another image in the same paper of 3C279, which is an active galactic nuclei that also has a black hole in it, but we just can't see the Event Horizon scale structure. So but what you can see is the jets coming off of it, and we're imaging those jets at resolutions and wavelengths that we haven't been able to see before. And the reason we show that in the M87 papers is because we have to solve during the imaging for calibration effects, because the atmosphere and other things cause us to have kind of calibration issues that are really challenging for us. And it's one way for us to validate that some of the calibration was done correctly by independently imaging the 3C279 and M87 and checking to see the calibration was the same. So that's kind of one. So you can see the pictures that we have of 3C279. It's really cool. And since then there has been a paper that has come up specifically on that and the time variability seen in 3C279. We also look at other AGN, and yeah, hopefully publishing work on those as well soon.
Okay.
Oh, I don't know, Nitika, I don't know if, I think there's also some work on pulsars as well. I don't know if you have any background knowledge on that. I think I saw.
So I personally do not have any background knowledge on pulsars and magnetars and all of that. But there are a lot of projects at OVRO right now that are specifically working on searching for pulsed emissions, specifically from this phenomenon called FRBs. And there was actually a really, really fantastic press release from a member of our group named Chris Bohenik. It came out just a few days ago and was all over like NASA, National Geographic, BBC, but he has this really awesome telescope out at OVRO called STARE-2, and its entire goal was to look for fast radio bursts from within our galaxy. And he ended up back in March or April, back in the spring, basically, he ended up finding for the first time a fast radio burst within our galaxy that was localized to a magnetar. And so there's been a lot of bustle around that recently.
Can you tell us what a magnetar is?
Yes, I can. So if we back up, we have massive stars, and then at the end of their lifetimes, they will, this is a very short story, of course, of what goes on, but for massive stars, at the end of their lifetime, they will explode in this phenomenon called a supernova. And for stars that are not really massive, so stars that are incredibly massive will leave black hole remnants, but the slightly less massive stars, and I'm just riffing here a little bit because I'm forgetting the exact numbers for these boundaries.
Riff away.
But so these like intermediate mass stars, they'll leave behind these remnants called neutron stars that are just these like incredibly dense stars. I think I saw a statistic once to help people understand how dense they are, that if you took a teaspoon of a neutron star, it would weigh more than New York City. So that's how dense these objects are. And so then a magnetar is basically a neutron star with an incredibly high magnetic field around it. And so for a long time, there were these phenomenon called fast radio bursts that people saw these like millisecond bursts in their telescopes. And for a while, people said, you know, that's probably just like interference from the Earth. It's probably like a radio station or a TV or something like that. But then they were seen at so many different telescopes that they were determined to be real, but nobody knew what they were because they were only ever seen outside of the Milky Way. But so for the first time this year, one was detected inside the Milky Way and was localized to this region around a known magnetar in the Milky Way. So it's an exciting time to be studying this field because for the first time, people are figuring out what the origins might be.
And notably, for our audience members, Chris Bohenik, who was the student Nitika was referencing, was on our Astronomy on Tap 2 weeks ago, talking about this very discovery before the press releases were out. So you should definitely check it out if you're interested. It's on our YouTube channel, our last Astronomy on Tap. Sorry, I'm cutting out crappy hotel internet. Okay. Penelope age 9 asks, does the black hole have to be circular or can it be a more irregular shape? I guess, yeah, maybe this is in reference to the singularity. Like Jordan was saying, rotating have a ring, but can you have more irregular shapes than that depending on, well, I guess black holes have no hair, so maybe not.
So this question I think is that is nice because it has sort of a lot of different pieces to it, right? That there's the question of what the singularity structure should be, and there's only a couple of ways in which that can look. What the event horizon shape is, and the answer is that curiously enough, both for the rotating black holes and for the Schwarzschild black holes, the non-rotating ones, the event horizon is spherical. But then the really fun part is what happens to the shadow. That I think Katie can talk about a bit.
Yeah. Yeah, so really good question, Penelope, right? I think it's Penelope. Yeah, so for the shadow, it does, sometimes it'll get a little squished on one side. So if you're viewing it, the black hole edge on, So you kind of, this gas that is spinning around it is like this. And you're looking at this ring of light that is being bent around the black hole. If you have certain parameters of the black hole, it will squish it more on one side, and you'll kind of get so it'll kind of change the shape of that ring a little bit. So yeah, definitely you can get different kind of shadow shapes, and that's what we're really trying to detect. So if we want to study, for instance, how we want to see how much is it squished, and does that correspond with the amount of squishedness we'd expect for the spin that we know of that has been constrained, for instance, from other methods. For instance, by watching these stars orbiting the Sagittarius star in the center of our galaxy. So, yeah, good question.
Yeah, that's cool. There's so many good questions here. Let's see. How about this one for Jordan? Since you work on calculating gravitational waveforms based on the mergers of black holes and other compact objects, what are gravitational waves?
Right, great. So gravitational waves describe these ripples that propagate in what is colloquially called the fabric of space-time. This is what we mean by this is there is a field that determines what the length scales associated with different objects in space-time. And the interesting thing here is that these gravitational waves are present only in Einstein's theory of general relativity, or small alterations thereof. They aren't present in Newtonian gravity. So the existence of these waves can tell us a lot about the fundamental theory of gravity, and, for instance, grant us all of these spectacularly tight constraints on how close the gravitational theory that we observe in, say, binary black hole collisions resembles Einstein's theory.
Fair enough. Awesome. Thank you. Yeah, and for those people who were paying attention in the last week to non-election based stuff like science, like the FRB result and the magnetar, there was also a release of a bunch of new mergers from the LIGO consortium. Do you guys remember how many? It was like 50 new mergers and gravitational wave detections of merging black holes. It was some very large number.
Yeah, thereabouts, 40 some, yes.
Yeah. That's super cool. That's super exciting. That it's gone from, in 5 years, it's gone from not being able to detect one to being like detecting 50 odd detections and just going up from there.
Right, yeah. Just a short while ago, there was enormous fanfare about every announced event, and now it's sort of routine in the yearly dump. Yeah, we got dozens. There you go.
Like everyone remembers, like, oh, I remember when, I don't know, when some big event happened. I remember when I watched the LIGO press conference. It was such a memorable thing, such an exciting event.
There was a question related to gravitational waves in that, can they redshift in the same way that light can redshift?
Yes, they can, though there's slightly different calculations that need to be made, but the basic answer is we still have the gravitational radiation, and depending on the approximation that we use, which makes this a little bit finicky, but if the gravitational radiation is of a fast frequency compared to the effect that would redshift it will have a frequency shift similar to electromagnetic radiation. The caveats there are that there's a lot of systems that will redshift electromagnetic radiation somewhat differently to gravitational radiation, just because the electromagnetic radiation tends to be of a far finer length scale than gravitational radiation from a realistic system.
There's a ton of gravitational wave questions. Can anything stop a gravitational wave other than another gravitational wave? But it seems like even another gravitation, they're waves, so they'll superimpose, they'll travel through each other.
Mostly. So there's the, there's caveats to everything I say, but so gravity is nonlinear theory. So technically, two passing waves will interact very slightly, but only technically and only very slightly. So they won't be stopped by that. They won't be stopped by matter, primarily just because gravitational radiation interacts so spectacularly weakly with matter. In caveats to everything I say, the energy does come from somewhere. When, for instance, there's this, you can imagine the gravitational radiation pushes and pulls on, say, masses on a string, and the energy to move those masses around did come from somewhere, and it came from the gravitational wave. And you do lose some of the energy from the gravitational wave after it passes, but it's attenuated so spectacularly poorly, and there's so much energy in the gravitational radiation for the systems that, for instance, LIGO studies, that the effect is completely negligible.
I see. So theoretically, you could have, like, in the same way that you can get a big bar of lead, a wall of lead to block X-rays. Like when you go and get an X-ray at the doctor, you wear your like lead apron. You could have an enormous thick, again, theoretically, enormous thick piece of matter. We'll say a 10 light year thick or 100,000 light year thick piece of matter that would slowly attenuate down that gravitational wave, but it would have to be hugely massive because it just doesn't affect the matter that much.
Right. I don't even, I'm not sure I would have any sort of good estimate for
That's okay.
how large a piece of matter you would need or how best to construct it, just that it would be infeasible in scale.
I see. Bless you. But practically, there's no way to stop a gravitational wave.
Oh, Leo Stein has the.
Oh, is Leo chiming in?
Leo is chiming in. I don't know when Leo chimes
okay.
in.
So
they are absorbed by black holes. This is true.
Leo Stein is a former member of our department at Caltech. He is now a professor at, I'm going to mess this up. He's in the
Ole Miss.
State of Mississippi, and he's either at University of Mississippi or Ole Miss. He's at Ole Miss. Okay. But he does a lot of work on gravitational waves and black holes as well. So he says the best way to stop a gravitational wave is for it to be absorbed into a black hole. Okay. Okay. So again, not very practical for us to block gravitational waves to align
black holes.
Yeah. But it is possible. Okay. Yeah, and I guess related to that, now we're getting really deep into the weeds. Would we expect concentrations of dark matter or black holes to refract and cause like refraction or diffraction as the gravitational waves kind of like bend around these structures? It seems like since they're waves, then presumably yes. But again, for all practical applications, maybe this is just a theoretical prediction.
There is actually a good question there that is sort of still an open research question, and that's the question of how practical black holes and the inspirals we calculate are affected precisely on cosmological scales by cosmological densities of matter or dark matter, and we don't currently run simulations like that, and that's probably something that we would like to investigate better. It's probably, I think, a fairly small effect, but we're getting to the point where small effects in gravitational waveforms are important.
Wait, so you're saying we could pick up the structure of the cosmic web, potentially pick up a signature of the structure of the cosmic web from gravitational waves kind of diffracting through it?
That's far more ambitious than I was thinking. I'm just thinking distinguishing
okay.
in the gravitational wave signal between whether you're in a, there's like words that I don't know how to define for audio, and a space-time that represents something that has sort of clouds of matter throughout it, or clouds of dark matter through it. These are known in the literature as FRLW spacetimes, which is not a helpful acronym because it lists off authors.
I see. So describing the distribution of matter as either foggy
Right,
or humpy.
so these spacetimes just model the matter as just completely homogeneous throughout the spacetime. And my statement is that we don't even yet completely know how the gravitational waveform from events that we are interested in are altered by a completely homogeneous cloud of matter between us and them, let alone the detailed structure depending on the precise sky location.
Okay. Okay. Let's do one more question. We're at the end of our time here, but I feel like we need to get back to one more question about black holes before we end here. So, well, Katie, you mentioned, actually this can be broader. Katie, you mentioned trying to get bigger baselines for the Event Horizon Telescope and space-based baselines, space-based radio telescopes. And maybe you mentioned this. What about the moon, which also ties into, like, I know in radio astronomy, and Nitika can potentially talk about this, we've always wanted to have radio telescopes on the far side of the moon, so we're not getting radio frequency interference from all of the stuff, all of our cable TV news networks and such. But has there been any discussion within the EHT consortium about the benefit of doing something from that kind of a baseline?
Yeah, so I think I touched on this a little bit earlier, but if you put a telescope on the moon, then you'll have a really long baseline. And the longer your baseline, the more kind of fine structure you're able to see in the image, but you don't get the broad structure. So putting something, well, on the moon or at a distance like the moon or a far orbit, we would be able to probe some information about the event horizon scale structure of not just Sagittarius Star and M87, but other black holes like Cene and other ones that we think will become that are a little smaller, so we can't get them with Earth-based baselines. But if we go to space, we would be able to see them. But we wouldn't be able to make images unless we have kind of intermediate baselines. So if we had not constellations, but if we had like telescopes at multiple different baselines in space, then we could make really high resolution images. But if just with one, it's more of a just extract like a model fit. Yeah, but Nitika, I don't know if you want to talk more about Greg's, the far side stuff.
Well, I think that there's not too much more left to say about it because it's still very much in its early phases, and especially at these lower frequencies, you're never going to get, so at 10 megahertz, for example, you're never going to get anything as high resolution or anywhere near as high resolution as the EHT. And the main motivation for putting this telescope on the moon and not on Earth is because the Earth's atmosphere will block out radio emission that I think below somewhere around 100 megahertz, you won't be able to observe from Earth anymore because of the atmosphere, which was one of the motivations for moving it to the moon. And the types of emission that Greg is hoping to detect with his telescope are like its magnetic emission from planets and stars, and it's quite faint. And so you need as high sensitivity as possible to detect it. And so the moon is a really good place for that. Plus, as Cameron mentioned earlier, it's totally free of, well, I don't know if I should say totally, but a lot more free of radio interference from stuff like power lines and cable TV and all of that.
Which is like the light pollution of the radio world.
Yes.
So, okay, great. Well, thank you. First of all, thank you very much, Katie, for your presentation,
Thanks for inviting me.
and thank you also to Nitika and Jordan for your expertise on the panel. It was great. Audience members, sorry about my crummy internet connection. I promise I'll fix it for next time. And our next event should be in a few weeks. I'll post it on social media and such. But we'll have Astronomy on Tap probably after Thanksgiving. And then first week in December, we'll have another stargazing lecture. So hope you guys get a chance to look out in the night sky and see one of the various cool objects that are up there. And we'll see you next month. Thanks, everybody.
Thanks, Cameron.
Yeah. Okay. We're ended. I know it still says live, but oh, need